As a pilot, you need to know before you take off that the airplane will have sufficient performance to complete the planned trip in the expected conditions. How much runway will you need to take off? What cruise airspeed will the airplane achieve? How much fuel will it consume? How much runway will you need when it's time to land? In this lesson on performance and limitations, we'll talk about how to determine what the airplane is and is not capable of doing. I'll start by talking about what you will find in the pilot's operating handbook and how to interpret that information. Then we'll talk about the limitations that are associated with your airplane as part of the certification of that airplane. Then we'll talk about the load factor versus speed chart and what information you can determine from that chart. Then we'll talk about the concept of density altitude and how that influences performance. Then we'll go through the takeoff performance, the landing performance, and the cruise performance calculations. In some pilots' operating handbooks, these performance numbers are presented in the form of tables. In other pilots' operating handbooks, they're presented in the form of graphs. So we'll go through some examples of each so that you know how to use both types. Since the 1970s, aircraft manufacturers have adopted a standard template for producing their pilots' operating handbooks. So you will generally find these same 9 chapters in all pilots' operating handbooks. These information, some of it is advisory, although it's generally good advice. You're not required to do what the manufacturer recommends. Other portions of the pilot operating handbook are mandatory. One regulation that we operate under, 91.9, makes it a requirement that you comply with the operating limitations specified in the approved airplane flight manual. So an airplane flight manual is material that's approved as part of the certification process. The airplane flight manual is included within the pilot's operating handbook, but the pilot's operating handbook also has some other information. So the parts of the pilot's operating handbook that are mandatory is Section 2 on limitations, and much of the information that would be in Section 9, which are supplements. Those generally relate to limitations that are related to optional equipment in the airplane. There are several types of limitations that are very common to find in Section 2. These include the required placards and instrument markings, the weight limit and center of gravity limitations, speed limitations. There'll almost always be a never exceed speed limitation. Most airplanes with flaps have a flap extended limitation. Others may have additional limitations like the maximum speed that you can have the windows open, things like that. Engine limitations. There will usually be a maximum engine speed, and there may be maximum engine temperatures. Approved or prohibited maneuvers. For example, some aircraft are approved for intentional spins, other aircraft are not. Load factors. Some aircraft are certified up to, say, 3.8 load G's for loading. Others, it may be a higher number. Approved fuels. Can you use less than 100 low lead fuel in this airplane? Some airplanes are approved for automotive fuel, sometimes with a restriction that it not have alcohol in it. So manufacturers can put whatever limitations in the limitations section that they feel like they need to in order to get through certification, and you're stuck with it. If the limitations section says that no flying on Wednesdays, then it would be illegal to fly that plane on Wednesdays. I don't know why they would make a rule like that, but whatever rule they make, you are obligated to follow those limitations. Our next topic is how to interpret a load factor versus speed chart. As the name suggests, this chart has airspeed on one axis and load factor on the other axis. Load factors are sometimes referred to as G loads. When you're operating in straight and level flight, you're operating with a load factor of 1 or 1G. When you pull back on the yoke or the stick, then you're operating at a load factor higher than 1. If you push forward on the yoke or stick so that you're basically weightless in your seat, that would be 0 Gs. And if you push further forward so that you're actually pushed up against the seat belts, that would be negative Gs. This chart shows various operating regimes that an airplane can be operated in. The curved line on this chart represents the maximum load factor that the wing can generate at a given speed without stalling. The curved line along the bottom represents the most negative load that the wing can generate without stalling. Since most airplanes are optimized for flying right side up, these two curves may not be exactly a mirror image of one another. Where the stall speed curve crosses the 1G load line, that point labeled B here represents the normal stall speed for the airplane. So the regions in the upper left and lower left on this chart are regions that the airplane is physically incapable of getting to because the wing would stall rather than create that much load. Aircraft are certified based on a maximum load factor, both positive and negative, for the structure. In this case, the aircraft is certified at 4.4 positive Gs and negative 1.8 Gs. On the load factor versus speed chart, these levels are indicated as the boundary between the green area and the orange area. The maneuvering speed is the intersection of the stall speed line and the G limit line. So if you're operating below maneuvering speed, a single pull on the stick will not cause the airplane to go over its maximum certificated load limit. So below that line, you're much more safe from unexpectedly exceeding the load limit on the airplane. Note that the stall speed line is calculated based on the airplane being at maximum gross weight. If you're operating at a weight less than that, then that stall speed line will shift to the left. So both your stall speed and your maneuvering speed decrease when the aircraft is more lightly loaded. The diagonal lines on this chart, the blue dotted lines, represent vertical gusts starting from normal straight and level flight. So when you encounter a vertical gust, it can cause either a increase in load factor or a decrease in load factor, depending on whether the gust is an upward gust or a downward gust. The manufacturer sets a speed limit called the maximum structural cruising speed that the aircraft should be operated in when you are that you should not operate in unless you're in smooth air. So if you're in gusty conditions, you want to stay below that speed. That speed is shown as the boundary between the green arc and the yellow arc on your airspeed indicator. And a factor that manufacturers often will use to set this limit is to make sure that a vertical gust up to a certain level will not cause structural failure. The right-hand boundary of the caution region is the never exceed speed. That is the speed that the aircraft should not exceed even when you're in smooth air. Sometimes the manufacturer will define VNE as a particular indicated airspeed. In other cases, VNE will be defined as a particular true airspeed. You should know for your aircraft which way it is, so that if it's a true airspeed, you need to be aware of what true airspeed you're operating at anytime you're anywhere close to it. Before we get into talking about calculations of takeoff distance and landing distance, I'd like to discuss this concept of density altitude. So density altitude is actually a measure of air density, not a measure of altitude. More precisely, it's the altitude within a standard atmosphere model at which the density would be equal to the current air density. The equation for lift is shown here, and one of the primary things that determines the amount of lift that a wing can produce is density. It uses the Greek letter rho. So as a result, since you need a certain amount of lift in order to fly, something else has to change if the air density is low. So when the air density is low, the velocity has to be higher. That means that the true airspeed for takeoff or the true airspeed during your landing approach will be higher when the air density is low. And since it takes a longer distance to accelerate to that higher speed, that makes your takeoff distance longer. And since it takes longer to slow down from that speed, it takes more distance to slow down from that speed, your landing distances get higher. If you have a non-turbocharged engine, then density altitude will also impact your takeoff performance for a second reason, which is that your engine will produce less horsepower when the density is high, or density is low, density altitude is high. The way we generally calculate air density is based on the pressure altitude and the temperature. Humidity has a minor effect, and we usually ignore that in our calculations of density altitude. So using this chart on the left, if the current temperature was 70 degrees, we would find 70 degrees Fahrenheit along the bottom, and we would go up vertically until we get to the line corresponding to our current altitude, pressure altitude. So in this example, I went up to 5,000 feet. Then we go over to the left and we read off that scale what the density altitude is. Looks like about 66 or 6,700 feet. So the density altitude in this situation would be higher than the pressure altitude, but our performance would be similar to the performance that you would normally get at 6,700 feet instead of the performance you get at 5,000 feet. So when we'd like to calculate the takeoff distance, and then we want to compare that to the amount of runway that we have available at our departure airport. So in the pilot's operating handbook that I pulled this chart from, there were actually several different tables like the one shown here each corresponding to different loaded weights. So you have to first find the correct table, and then you have to look up your takeoff distance in the table. To do a conservative calculation, you can just round up to the next highest weight to pick the correct table, and then round up to the next highest altitude and the next highest temperature, since takeoff distance increases with all of those variables, and then look up your value and compare that to the runway available. If it's significantly less than what you have available, then you're in good shape. Notice that the table tells you the ground roll, and it also tells you the distance required to make it over a 50-foot tall obstacle. So if your runway that you're going to be using has a clear departure path with no obstacles, then your only concern is the ground roll. If you have an obstacle, then you have to figure out how much distance it's going to take you to clear that obstacle. If the obstacle is some height other than 50 feet, then you should look at the difference between the ground roll and the 50-foot number and scale accordingly to the height of the actual obstacle you have. If you need to be more precise in your calculations, then instead of just rounding everything up, you need to use interpolation. So here's how you do an interpolation. Suppose that we want to calculate our takeoff distance at an altitude of 3,200 feet with a temperature of 14 degrees Celsius. Those numbers don't appear in this chart. They fall between numbers in the chart. So we create a mini table that has the numbers surrounding that. So I take the 3,000 and the 4,000 foot numbers, I take the 10 degree and the 20 degree numbers, and I get a little table as shown here for those numbers. The actual altitude is 20% of the way between the tabulated values, so I have a 0.2 weighting factor on the 4,000 foot numbers and a 0.8 weight value for the numbers that correspond to 3,000 feet. You give a higher weight to the one it's closer to. The actual temperature is 40% of the way between the tabulated values, so I'll give a 60% weight to the 10 degree numbers and a 40% weight to the 20 degree numbers. So I multiply these numbers out with those weight values, and I come up with 902 feet as the distance required for takeoff under that altitude and that temperature. Now notice in this particular POH, they tabulated it as a function of pressure, altitude, and temperature. In other POHs, they could do it differently. They might have you first do a calculation of density altitude and then tabulate the takeoff and landing distances based on density altitude without a temperature. So weight and altitude and temperature are not the only factors that influence your takeoff distance. The takeoff distance will also be influenced by the condition of the runway gradient, wind. So a common thing you'll find in POH calculations is they'll give you correction factors to account for those things. So these notes appear somewhere near the tables, and they give us things like for 9 knots of headwind, we decrease the takeoff distance by 10%, but we increase the takeoff distance for every 2 knots of tailwind. Notice that tailwind increases it a lot more severely than what headwind helps it. If the runway surface is something other than a paved runway, for example, if it's a dry grass runway, then we need to increase the takeoff distance by 15%. So applying these factors, if we were using a grass runway and we had a 4-knot tailwind, we would multiply our 902 feet by 1.15, which is our 15% correction factor for a grass runway, and 1.2, which is our correction factor for the 4 knots of tailwind, and we get 1,245 feet. Next, we need to calculate the landing distance so that we can compare that to the amount of runway available at our destination airport. Your POH may have charts, just like we used for takeoff distance, or some POHs present the information with graphs instead of charts. So we will use that method to illustrate the landing distance calculation. In this chart, the first part of the graph is basically a density altitude lookup. You'll find the current outdoor temperature in the bottom and draw a line vertically until you get to the current pressure altitude, and then you'll follow horizontally to the right to get to the second part of the graph. The second part of the graph is where we correct for loaded weight. To do that, we'll draw a diagonal line that's parallel to these solid lines on the graph, and we'll start that line from where our density altitude came out. Then we'll find our loaded weight along the bottom and draw a vertical line along that until we intersect that diagonal line that we just drew. And then we'll follow horizontally from that intersection point over to the third part of the graph. The third part of the graph is where we will correct for the amount of wind. So this is a similar method. We'll draw a diagonal line starting from our previous point, parallel to the lines in the graph. We'll find our current headwind or tailwind component. So in this case, we have a headwind, so we're using the downward sloping diagonal lines. If we had a tailwind, we would be using the upward sloping diagonal lines. So we draw a line up until we reach the diagonal line. Then we follow horizontally from that intersection point, and then we read the landing ground roll off from this chart. So in this case, it looks like our landing distance would be about 825 feet. So there will be another chart that'll allow you to calculate your landing ground roll over a 50-foot obstacle, and you'll use that number similarly if you have a obstacle in your approach path. Landing distances tend to be a lot more pilot skill dependent than takeoff distance. So you need to have a little bit more margin of error in between your calculated landing distance and your actual runway length than what you might need for takeoff. And just like there were correction factors for the chart method that we used during takeoff performance, there may be correction factors for landing distance that we would use in the same way. In order to plan our flight to make sure that we will have enough fuel on board, we also want to look at the airplane's performance during cruise. In particular, we want to know what kind of true airspeed we should expect, and we want to know what kind of fuel flow we should plan for. These vary as a function of altitude, temperature, and the engine speed you select. For if you have a controllable pitch propeller, it will be a combination of engine speed and manifold pressure. And we'll find this information in the performance section of the POH, either in a table as illustrated here or in a graph form. And we use this in the same general way we use the tables for takeoff and landing performance. Notice in this case, the temperature is not an absolute number, but instead is a temperature relative to the standard temperature for that altitude. These tables make some assumptions about how you're operating your engine. In particular, they make some assumptions about how you're going to lean the engine. So if you're not leaning your engine properly, you may be burning more fuel than what is predicted by these tables, and you may not make it as far as what your calculations indicate you should. In addition to these kind of charts, your POH will have other tables or charts to indicate climb performance, descent performance, and some other performance calculations. You need to, when you're using them, you just need to make sure you're paying attention to which variables you have to use to do the table lookups or the graph lookups, and you have to make sure that you are applying the correction factors after you've done your initial calculation. That concludes the lesson on performance and limitations. In order to apply this information to the aircraft that you are using for your flight training, I recommend that you work with your flight instructor and get out the pilot's operating handbook for the airplane that you're using. And as a first step, you should read through everything in the limitations section. Make sure you're fully aware of the limitations that apply in that aircraft. Then, on a day that you're going to be practicing short field takeoffs and landings, you should calculate the required distances for the current conditions on that day and determine what you should expect to be how much runway you should expect to be using for your takeoffs and your landings. Then after the lesson, compare that with the results that you actually achieve flying the airplane.